So Greg, please take it away about your presentation on Ruskin.
Okay, thanks, Eric. So I think my title slide is up at the moment, and I'm just going to fiddle a second to get rid of a few other bits of clutter. Ruskin is the only piece of software that RBR makes. We have done so in one version or another, and I think there have been quite a few versions that have been released over the last decade. And you'll find that it runs equally well on a Mac or a PC. We also have a version that's slimmed down slightly that runs on both iOS and Android versions. It's the only instrument software that we make because it talks to every instrument we make. And so every instrument we've made in the last 15 years or so can be spoken to with Ruskin. We know that our instruments have a long life cycle, and we know that people still ask for them to be calibrated after that amount of time and to do some minor servicing on them. So we're happy to see that they don't end up in landfill after a couple of years. One of the reasons that it is so powerful for people as users, but also either before they're a user or even while the instrument is already deployed, is that we're able to simulate the deployment of any of our instruments in Ruskin without the physical instrument being around. So I'll show you a bit about that today. It's very useful for predicting the autonomy of the instrument, how long it's going to last at the sampling rates or the sensor payload that it has attached. It has, of course, what we take for granted nowadays, which is completely automatic update. And those of you who have been running it in the last few days will have seen that we've just done one of the new releases. And it also carries with it, as a kind of sidecar payload, all of our documentation. The documentation we internally call RUGs, which are Ruskin user guides. So whether those are for our compact 1-inch diameter, 25mm diameter instruments, or for our slightly larger standard instruments, which are about 65mm in diameter. All of the documentation in PDF form is carried inside Ruskin. It also carries what we call the RIGs, which are the RBR instrument guides, so specific guides for each instrument that we're developing at the moment. So we want to make sure it's kind of the single place you can go to get all that help. I jumped over the other very common thing that really should be essential in software today is that although we're privileged as native English speakers, that English is currently the lingua franca of the world, of course it's very helpful as a user to have Ruskin speak your own language. And so we have translations. Ruskin will run in about 6 or 7 different languages. And we work hard to try and maintain those translations to make sure that they're as accurate as possible. We try to have a new release of Ruskin about every 3 months, 4 times a year or so. And usually those are comprised of a mix of support for new instruments that we've developed, new features for existing instruments. A bit like a Tesla car, you might obtain the hardware, but we want to improve the instrument behavior over time. So when we find ways to reduce the power consumption via firmware, then we are able to do that in a Ruskin release. And of course, if we find any bugs or irritants, we're able to fix those as well. So I think the title was something about pro tips, but I'm really going to run through a kind of A to Z of using Ruskin. First question is, where do you find it? And you find it for free on our website. You don't need to have an RBR instrument to use it. As I said, you can simulate any of our instruments. And so if you go to rbr-global.com/product/software, you can find there the Ruskin for Mac and PCs and the links to the Android Google Play and to the Apple App Store. In addition, we have another piece of software that's used for more sophisticated post-processing, which is the RSK Tools toolbox. That's actually designed for MATLAB users. And we'll be talking a bit about why our files can be used in MATLAB without any conversion a bit later on. But RSK Tools, even if you're not a MATLAB user and you prefer to do post-processing in R or Python or other tools, looking at RSK Tools will give you some ideas on how to open those files. You can see on the left here, the installer is very simple. You just grab the Ruskin icon and pull it over into your applications folder, or double click on the installer if you're on a PC. So in terms of connecting Ruskin, once you've got it to the instruments, I brought a couple of instruments along, as you'd expect. So this is a Solo T, our single channel temperature recorder. It runs off a single AA battery, and it has a USB-C connector on it. And so with a USB-C cable, you can plug that in. Now, I've got a Mac on me today, so it's got USB-C on the other end, but when we supply the instruments, they come with the older Type A socket on them as well. So we can clearly talk to any instrument, whether it's the small compact one or a larger instrument like our Concerto CTD, that also has USB-C on the end of it. However, with the standard instruments, we also have a second port in here, and that exposes RS-232 and 485. Although we moved to USB as the kind of standard desktop connection about 8-9 years ago, RS-232 and 485 are still necessary for underwater connections to other bits of equipment. It might be talking to the float or the glider. It might be talking to an underwater Campbell logger that you've got, for instance, that you want to move the data to. And so RS-232 for up to 50 meters and 485 for much longer. We've made 485 cables, I think, about 500 meters in length. Those are built into every one of our standard instruments, and Ruskin will do auto discovery over the serial protocols, so you don't need to know anything about the baud rate or the ports. You simply plug the instrument into your computer with a dongle, and we will find it. On all of our standard instruments in the last couple of years, Wi-Fi has been available as an option, and it's actually buried inside the instrument. And so Ruskin can talk over the Wi-Fi adapter of your laptop or desktop to speak to those instruments. And if you've got any Ethernet connected instruments, maybe they're on an observatory, maybe you have a serial to Ethernet dongle in your lab and you're using our CTD to monitor some tanks, then Ruskin will talk over an Ethernet socket as well to talk to them. And that's really the transport layer, which is an electrical difference. But clearly, the protocol that we use is absolutely identical. And so if you don't want to use Ruskin at all, and you'd like to just talk to the instrument using a serial command line, you can do that yourself, no problems at all. So then we get into the question of, well, how do I connect to an instrument if I don't have the instrument? Maybe you don't have one because you're talking to somebody at RBR about trying one of our instruments for the first time. Maybe you've already deployed the instrument, or it's in your lab and you're stuck at home and you want to think about how to use the instrument. And so at this point, I'm going to try and see if I can switch over to showing you Ruskin itself. And let me see if I can do that, and we'll go into a little bit of a demonstration. And of course, as luck would have it, something always goes slightly funny. There we go. So I've flipped over to Ruskin now. I hope somebody will let me know if you cannot see Ruskin. I think you should be able to do that at the moment.
Looks good, Greg.
And so, great, thanks, Eric. So we've got Ruskin, which is a very simple app divided in the classical format into a kind of navigator on the left-hand side, an editor on the right that shows you whatever instrument or data set you've got selected on the left, and this charting window at the bottom. We can connect to many instruments at once, limited only by the number of ports that you have on your machine, or the amount of mental confusion you can have as to which instrument you're doing what with, and you can open many data sets. Now, we were talking about simulating. So I've simulated a couple of instruments here because today I've actually used all my ports for a variety of monitors that I have set up. But I'm going to show you how to simulate an instrument as well. So under the Instruments menu, you can go into Simulate an Instrument, And you can simulate any instrument that RBR makes. So we have here, I showed you in my hand a little bit earlier, the compact Solo T instrument, which is just a single channel temperature recorder. And we could simulate one of those. We can simulate our pressure instrument, or maybe the optode that we make. We can also simulate more sophisticated instruments in our standard grouping, like a CTD. And maybe we'd want to add a optode to that, or a turbidity sensor from, let's say, C-point, that kind of thing. So we can do that here. And we can also add a variety of options, such as the sample rate, the maximum sample rate that the instrument can do. In our quartz family, which are all based on parascientific quartz pressure gauges, you can simulate the quartz Q, the quartz BPR, or the new BPR0, which implements the A0A technique for getting rid of drift. You can also simulate our older instruments from years gone by. So some of you might have a TR1060 in your lab. I think the last time we built those was about 2010 or so, maybe 2011. However, it's still worthwhile being able to simulate them, and of course.
Quick interruption. For some reason, we still see your main Ruskin page, but we're not seeing the pop-ups. They're not like the ones you're simulating. We're not seeing that, unfortunately.
Let me. I think the screen share needs to be flipped to desktop. Is that better?
Yes, we can see it now.
Okay, so I'll go back slightly. All right, so I got in here by going up to instruments and simulate an instrument, and then it opened this second dialog box, which you've all been very politely, or not so politely, seeing as I don't see the chat, waiting to see when it would pop up. So here are the compact instruments. Here are the standard instruments, where we're able to add additional channels, for instance. And here are the quartz instruments for the Q, BPR, and BPR0. And skipping over sensors, but looking at some of our vintage instruments, the oldies but goodies, the 1060, 1050 class, the old XR and XRX series. So this allows you to simulate any instrument, and in the manner of an English cooking show, here are three I prepared earlier. So this is what happens when either you simulate an RBR Solo T or you attach it. The only difference here is that the simulated ones have the word sim prefixed to them so that you can differentiate. So in this right-hand side, we see the basic parameters that you need to use to set up the instrument. And this forms part of, let me see if I can stop that occurring. This forms part of what we call our autonomy engine. This is the practice of Ruskin that allows you to estimate, as you can see where my mouse is, how long the deployment will last given the sampling conditions that you've requested. So we have an instrument here that's not currently enabled, it's not running at the moment. We can do a variety of things with it, but I think I'm going to concentrate first on just talking about batteries. Batteries are a subject of considerable debate and concern for people. And I think you can see a little bit of video of me. And I'm going to show you that RBR instruments actually support any AA battery. So I have on my desk here the classic AA that we ship with every instrument. And that is the Tadiran in this rather fetching color of purple. This is probably the best battery we know about. It's lithium thionyl chloride. And one of the very nice things about it is that it doesn't have any kind of attitude problem. And the attitude problem is one which refers to the fact that lithium thionyl chloride batteries, when they are put in cold water or cold temperatures and kept very still, and have the positive anode facing down, the electrolyte can settle inside and it passivates over the anode, and you lose some capacity. And this can be very disturbing if you're doing an Arctic deployment, because you'll find that you lose 30 or 40% of your battery capacity. And I want to hold up the battery, which is the worst for this. It is another manufacturer of lithium thionyl-chloride called Saft. And it's otherwise a very good battery. It's a Saft LS14500. Has all the same datasheet characteristics as the Tadiran, but if you put it upside down in cold water, you will actually find that it passivates, and those of you who have used this battery may have been bitten by that particular problem. So that's why we always ship with Tadirans. It means that the instrument orientation is not a problem at all. There are a few other manufacturers of lithium thionyl-chloride batteries. One of them is the Green Energy Battery Company, Gebsi. This is a Chinese manufacturer. We've evaluated this cell fairly extensively, and it is excellent. If it weren't for the fact that the Tadirans are very easy for us to get in Ottawa, we would probably move over to the Gebsi battery. However, for people in the Asia area, Gebsi are widely available. You have to buy them in a minimum quantity. Usually, I think it's about 100 at a time, but they're also a very good price, and the performance is excellent. So those are the three main lithium thionyl-chloride batteries. Now, when you don't have LTC batteries, there's usually there's usually one major reason for that, and that is that LTC batteries can be difficult to transport. They have to be transported either in the instrument or in separated packaging. You are not allowed to just throw 3 of them in a bag and get on an airplane. So they need to either be in blister packs or individual cardboard boxes, those kinds of things. And so that makes them difficult to transport. And so sometimes people would rather use the next best battery. And the next best battery is a lithium-ion battery. I'm holding here the Energizer Ultimate. Now, unlike the lithium thionyl-chlorides, which are about 3.6 volts per cell, lithium-ion batteries have actually got a circuit inside them which reduces them to 1.5 volts. So they are, in all aspects, a genuine drop-in for an alkaline battery. With lithium thionyl-chloride batteries, you must not drop them into your flashlight, your torch, other pieces of equipment, because the voltage is too high. RBR instruments are designed to deal with this high voltage, but that's not always the case. Lithium-ion is a very good second choice, because you can transport these with no limitations whatsoever. However, the capacity is about 50% of that of a lithium thionyl-chloride battery. Your next choice would be an alkaline battery. I was going to bring out the eponymous Duracell with the copper top, but I instead found an Amazon Basic battery. Alkaline batteries are very, very cheap to obtain, very easy. You can find them in the corner store. By all means, you can go ahead and deploy the instrument on alkaline batteries, but the capacity is about 30% of lithium thionyl-chlorides. For short-term deployments, absolutely no problems, and of course, available at the nearest corner store. There is a lithium-ion battery that's available. I didn't find one to show you today. The only manufacturer that we found of those in AA form factor is a slightly worrying company called UltraFire. And I'm not sure how many airlines are happy with you taking a battery called UltraFire into the cabin. So I don't have one of those to show you today, but we do have also support for rechargeable batteries in the form of nickel metal hydride. So I have 2 of those with me. One of them is the Panasonic Eneloop, which is very well reputed and can be found on Amazon and other kind of online stores. This is a equivalent, which is a Duracell. It has the copper top of the alkaline, but the green indicates, of course, the suggestion that you don't need to put these into landfill. And that's why we really wanted to support nickel metal hydride, even though their power capacity is quite low. It's only about 25% of a lithium thionyl-chloride. So it's only good for very short-term deployments or perhaps profiling applications where you're able to charge the batteries every night. However, because you can charge them for several hundred cycles, you really do reduce the amount of material flowing into landfill. And that's something that's important to do. Now, lithium thionyl chloride batteries do have one particular problem with them, and that is they're not capable of delivering high currents. So for instruments which are CTDs or Ts or Ds, that is conductivity, temperature, and depth, or some subset of that, LTC are fine. If you need to power optical sensors, then lithium ion is probably the way to go. Or you can use external batteries as well. And you can see in Ruskin, not on a solo, but if I look on a standard instrument, which is an instrument capable of having a connectorized end cap, we have a range of predefined options for the external battery. So I'm going to go back to the solo and talk about how to configure the instrument. So we start off, and you really work your way down this page before you get to this enable button that is what you'd like to do to deploy it. So first of all, we'd like to synchronize the clock. I can synchronize it to the local clock, which in this case is about just, it's in the middle of lunchtime, 12:27, and I am in UTC -4 at the moment. And so if I click on the local button, it'll sync to my clock. If I click on UTC, it will flip it over to Zulu or UTC time. And so you see it's running at 16:27 in the afternoon. You can then set a start time, and the start time might be sometime in the future, but it might equally well be that I just like to get going now, and I don't really mind when the time is. The end time, we don't actually let you set. We tell you when the end time will be according to how long the batteries or the memory will last. And so this is the core of the autonomy engine, is that in conjunction with the start time and the sampling rate that would be defined up here on the right, we can see that this instrument will, at 2 Hertz, run for 147 days. If I change that down to, let's say, 5 seconds, then you'll see it will run on batteries for just over 6 years. The second part of this bar is the additional capacity that is not the limiting factor. So you can see we have a little battery icon here that suggests that the battery will be the limiting factor on this deployment, but we have enough memory to run much longer at that sample rate. If I flip this over to running at 2 Hertz, you'll see the battery would limit us to 147 days, but we've got enough memory for a little bit more. Now, on some of the other instruments that we'll simulate, where they have optical sensors, the power consumption is much higher, and you'll see that little memory chip flips to being the limiting factor, and the battery becomes the reverse. These take into account the battery that you've told it you are using. So if I flip from lithium thionyl chloride to lithium ion, you will see the battery life drops commensurately. The total amount of samples that can be recorded in memory is identical. I can change the sampling mode from continuous according to the instrument to averaging or bursting or tidal waves. And in fact, we're going to have a webinar on June 17th about our wave instruments, so I won't talk about that too much today. In the case of this simple temperature recorder, it's only able to record continuously. If I flip over to a concerto CTD, then this instrument can be run. Let's say we were going to do, this is an instrument that's capable of running to 2 Hertz, but let's say we wanted to put it out on a mooring and run it at every 5 seconds. Every 5 seconds on the lithium ion batteries, oops, sorry, that was a rather slow changeover of my mouse. Here we go. So here is the concerto CTD on the mooring, and I look like I'd configured it to run every 30 seconds. And it will run on batteries for 8.5 years on those lithium thionyl chloride batteries. In the concerto for moorings, I can also do averaging. And when I do that, I can set up what is the actual sampling rate, how long would I like to average for as a duration, and how often would I like to make that average. I do have a couple of other features as well, which are available on the standard instruments, as well as just defining that we're going to start according to a date and a schedule. We could also have some additional what we refer to as gating. Gating is the ability to only start according to some secondary criteria being true. And the most common one is twist activation. Twist activation is seen on the end cap. If you look at my video for a second. So you will see that when the end cap is aligned in front of the pause signal, this instrument is actually completely consuming no power at all and can be put on the shelf for 6 months or a year with no penalty to the power, and then can be taken off and twisted into the play position. The instrument will vibrate in your hand, and it's now running. When we put it in twist activation, we don't really care when the start date will be, and we don't show you what our predicted end date is. We simply tell you that we should last for 8.5 years. So twist activation is very common if you want to give the instrument to somebody else to use, and just before they put it in the water, you'd like them to turn it on. Sometimes you're in the situation where you'd like it to turn on automatically when it hits the water, and so you can change the gating mode to be the marine wet switch. The marine wet switch is used when we have a conductivity cell, and it detects the salinity in the water and starts the instrument at that time. There are a couple of extra options that you see up here on the right-hand side. I'm not going to get into all of them, but perhaps the most important to look at is the real time. And that is to say that the instrument can behave as a logger, storing data internally, as you'd expect. But if it has an underwater cable attached, then we can stream data out. Over very short distances, you could stream USB. Over longer distances, as I mentioned, either the 232 up to 50 meters or RS-45 up to several hundred meters, you can stream serially. And that means that the instrument is spitting data out without being spoken to at all. You don't need to interactively ask the instrument for any details whatsoever. You can really just listen, and the instrument will send the data out at exactly the same rate that you told it to store it internally. I think that probably covers this section, so I'm going to see if I can flip back to PowerPoint. There we go. So the autonomy engine, these deratings that you can determine yourself when you look at the use of the batteries. We talked briefly about synchronizing the clock, starting now or later, a variety of different sampling modes. Now there's one that I didn't show you. Let me see if I can do that. And that is for a profiling instrument. So here I've simulated a concerto CTD that's able to run at 16 Hertz. And I'm going to show you, I was going to show you, but didn't set up my demonstration correctly. So I'm going to just pretend and talk to you instead about this directional sampling mode. Directional sampling mode is particularly useful when you're going to deploy the instrument on some kind of vehicle or body that's going to make it move through the water column up and down. So the instrument, particularly a CTD, always has a pressure sensor. And so if the instrument is moving up or down, let's say it's on a wire walker, or you might be towing it on an acrobat or some kind of towed body so that it's tow-yoing up through the water and up and down through the water, the instrument can actually tell which way it's going. And on a wire walker in particular, we always mount the sensor so that it gets good flow over the sensors when it's moving up. When it's moving down, the wire walker is actually quite jerky and not very clean platform for measuring. And so we don't want to waste a lot of power making a high-speed acquisition while we're going down. But of course, we can't predict in advance at what time of day or how often the wire walker will move up and down. And so the instrument itself can be told, well, When you're moving upwards, I'd like you to sample at 16 Hertz. When you're moving downwards, I'd like you to slow down and go to sleep, save lots of power, and only sample maybe once every 2 or 3 seconds. And that will result in a data set that has 2 different sample rates in it. And this is really trivial to do, and means that you save a tremendous amount of power. Usually upwards of 50% of the power can be saved that way. So we've deployed your instrument. We've hit that enable button. The instrument is now recording, and at some point you're going to come along and download. The download button is available. Let me just go over to here. So usually once the instrument is running, then this download button will be available for you. And when you select that, this little progress bar will fill up and the data will come out of the instrument. It's over USB typically that you're working on your desktop, so it's very quick. You can download over serial, of course, or Wi-Fi or Ethernet. There's no restriction on any of that behavior. However, I've got one instrument on my desk. However, we have a number of users who have 10 instruments, 100 instruments, even 1,000 instruments. And they would like to be able to download them without consuming a lot of time, especially when they're sitting on a boat with mouse clicks. And they can do that by setting up automatic tasks. Automatic tasks, such as auto download, allow us to recognize that an instrument has been connected and download it without any user interaction whatsoever. So simply by plugging in the instrument, Ruskin will generate a unique file name for it based on the serial number of the instrument and the time and day that you're downloading. Download the instrument. That means that you can plug the instruments in one after the other. This little green light that's on the that's currently yellow on these instruments will change to being red, meaning that it's busy downloading, and then green, meaning that it's okay to disconnect it. And you can then download as many instruments as you need to without having to touch the mouse or keyboard. The same is true, actually, when you go to deploying the instrument. So you can turn on auto deploy. Auto deploy means that if you deploy one instrument manually and then turn on auto deploy, then all future instruments that you attach will receive the same configuration. So you can set them, let's say I'd like to start at 1 o'clock in about 20 minutes, attach this instrument and say enable, turn on auto deploy, and then attach 100 other instruments of the same variety, and all of them will be set to the same sample rate, the same start time, the same gating, those kinds of parameters, and will be automatically handled. So just a little thing to try and make it efficient for people who are doing mass deployments. Once you've downloaded, then we're going to talk about the display. So I'll flip back to Ruskin again. And I'm going to show you some data from some other instruments that we've looked at earlier on. Let's see if I can do that. So this is the chart display that you typically get from a data set in Ruskin. And it's comprised of 2 parts. You have this thumbnail view at the bottom that is the entirety of the data set from the first point that you recorded to the last point that you recorded. And then you have this zoomed in section that's highlighted in a rectangle here and that we're able to move. And what you are zooming in on is shown in the expanded view above. So there's a couple of different things going on with this instrument that are nice little features. The first is, as you can tell, we're looking at temperature, depth, and salinity. And if we want to move around in the data set, yes, we can use the thumbnail as you saw, but I can also grab the time axis. So I can just grab the time axis and pull it across. And at the moment, we are zooming to the extents of the data. If I want to change the zoom of any particular channel, let's say I want to have a look at the depth signal when it's close to the surface, I can use the scroll bar on the mouse or to click and pan, and I can zoom in or out on that data at any time. I can always reset the zoom to being automatic and ranging to the data by clicking on this auto ranging button up here. I can also see these bars that are above the data, and these are what we call annotations. This is information about the data that isn't the actual sensor results itself. These annotations are profiles, and this instrument has been automatically detecting profiles. So even though it was deployed possibly by hand, by somebody who's doing variable data rates to drop the instrument into the water, I pull it over, especially into this, maybe with a fewer number, it's easier to see. So you can see here is the depth from 0. Oh, I take it back. They didn't deploy this by hand. At least if they did, that's a very unfortunate PhD student. That's a 2,600 meter deployment. So they deployed by on a winch or a rosette. They took the instrument down, they turned it around and put it back up. The instrument has automatically determined that that was a profile. And in addition, it split the profile into the downcast and the upcast. We can actually use the navigation features to move through the profile. So if I do profile by profile, you can see we're looking at profile 26 at the moment. I can jump and it will auto zoom to profile 27, 28, 29. Now, of course, you usually find that the data is only of decent quality in the direction where the water is hitting the sensors cleanly. So I'm going to assume that's the downcast, and we can shift to only looking at the downcasts instead. And so now we're just looking at the downcasts. What we might be more interested in is seeing a TS plot. And so I can flip over, instead of seeing the time axis, I can look at the depth plot. And I didn't pick this for particular clarity, but you can see here's the temperature profile as we go down to 1,800 meters. That's just a wobble at the surface that somebody's doing. And then here we are down to 2,200. So this ability to flip between the depth plot and the time series is quite effective. There are lots of other things that you can do in the charting, zooming through. You can also add your own annotations. So you can add a profile manually, or you can add a comment. So I can say, I'd like to put a comment in here where I dropped my phone. And that is persisted into the data set so that anybody who opens this again can find this location or navigate through. You can also put in GPS positions. So if you would like to annotate and add a position yourself, we can say first profile and put in the Latin long that comes from some other device. Or I can mark a region. Let me do that again, sorry. Or I can mark a region and I can say this all corresponds to a single GPS position, GPS 2. However, if the data set comes from Ruskin Mobile, or it has GPS positions of your manual entry, often you'll want to process this in your own equivalent downstream processing tool of your own. But here is an instrument that profile series that has 2,500 profiles. And these were deployed on a wire walker, and this little tag over here lets me open up a GPS map. This GPS map is probably going to struggle because it's going off to the network at the moment, and I'm using all the bandwidth, but you can see that we have many, many different profiles that were done in here. And as I zoom into them, we get to the point of individual ones, you see they become tags. So this is profile 1844, and that one is 1846. And when I select it, it changes the navigator to look at it. And in case you're wondering, well, where is this blue background, you'll see that we're actually in the Bay of Bengal. And this is a Wirewalker deployment that was done where the Wirewalker actually sat in a very large eddy and recorded 3,500 profiles as it moved over that time series. So this is fairly preliminary in terms of mapping, but it's useful to get an idea. And of course, that GPS data can be extracted in RSK tools or any other tool of your choice. I'm aware that I'm already 45 minutes in, and so I'd like to quickly go maybe to my next set, which is to talk about the RSK file itself. RSK files, if we open up the PowerPoint, it may come on screen again, we'll see. There we go. RSK files is just the extension name of the type of file created by Ruskin. And the world has enough file formats out in existence already that we didn't want to create another one. So even though you might not have heard of an RSK before, actually it's implemented as a SQLite file format. And that's a single file database that's used for many different applications and data stores. And you can read it with almost any programming language. So yes, we do have RSK tools, which helps you work with them in MATLAB, but you can read SQLite files natively from Python, from R, from Objective-C, Swift, no matter what. And so that schema is completely open, and we're happy to support you opening RSK files without needing to export them into an intermediate format. Now, we do have intermediate formats if you like, particularly if you don't want to read a SQLite file, but you'd like to look at a text file, then you can do that. So we'll export into text, and we'll export natively into Excel. The reason we do that natively is that the Excel export can have multiple sheets, one with just the data and one with the experimental or the deployment metadata. That makes it really easy to plot the entire block of data from top to bottom without having to wonder about where the data really starts. In terms of calibration, I'm going to jump back into Ruskin. I'm going to talk briefly about what an instrument looks like in terms of its calibration. We looked at this configuration page. The information page here tells you a little bit about the static information, like the serial number, the firmware version, how we're currently connected to it. Also, whenever you click this refresh icon, it will ask the instrument what its current battery voltage is. This instrument is running off USB, but it does have an internal battery at 3.6 volts. In the calibration page, we can look at the calibration coefficients. And so in this instrument, which only has a temperature channel, we can see those 4 coefficients are there. We could also modify them and store them back into the instrument. However, for CT and D, you really, if you want to obtain the best possible, if you want to maintain datasheet accuracy levels, you should be calibrating them every year. And so the calibration date is stored in the instrument as well. And once that instrument is more than 12 months old, when you connect the instrument, you'll find that this tab goes orange. And it will warn you that the CTD calibration has expired and you need to recalibrate. And in many countries, there are national labs which can do that. But if you wish to send it back to RBR, then you're more than welcome to do so. And by clicking on this button, you will then get a window that appears that informs you that this simulated instrument doesn't require it. But if you put in your name and your details, it's automatically figured out the serial number of the instrument and which calibration should be done. And you hit submit, and this goes into our ticketing system, and somebody can reply with a lead time on how to get it quoted and a quote for the recalibration. This summer, and most summers are usually not the time that people send it in for calibration. But this summer, of course, with people, this Northern Hemisphere summer, is a time when most ships are not going to sea. And so it's actually a good time to get those instruments that you've got in your lab serviced and recalibrated. And that's the easiest way of asking us about it. There are additional parameters that can be set, and these parameters are used in deriving additional channels. So I showed you on the CTD, which I had open a moment ago, that we were looking salinity, temperature, and pressure. But there are a number of other channels that the instrument is capable of recording. In fact, it natively records conductivity, or it measures conductivity and temperature and pressure. And these three are the core measured channels. The additional channels are what we call derived channels, including salinity. Salinity, as you know, is derived from the combination of CT and P, but depth is something we consider a derived channel. It's derived from pressure, and it's either done using a density of the water, or it's using the UNESCO approach from, I believe it's Tech Note 44, that allows you to punch in the latitude of the water. If you want specific conductivity or speed of sound, you can derive that as well. The instruments will derive them internally, or you can do them in Ruskin. Let me jump over to what happens if you've got a question. So I think I talked earlier about the Ruskin help guides, which are the Ruskin user guides are in here, and the instrument guides are over here. There's also a command reference if you're interested in talking to the instrument serially. But we also have this comment on Ruskin feature, and this is the most useful way of telling us you have got a problem. The reason for that is that you can put in your name and your email address, and failed to download instrument. I kept on clicking, but nothing happened. It means that you can also attach a screenshot if you've got one, which is great. But in addition, when you hit submit, having put in a name and email address, it will send us the log files from Ruskin, and those are most useful for telling us if something's gone wrong under the covers that we need to address. I think, I'm just going to have a quick look. I think that really covers most of the things that I've got time for today. And so I'm going to flip and stop sharing the screen if I can manage that, and move over to the questions. And I'd be happy to take them either verbally, or Eric, you can point me to the ones that have come in that still need answering. So I hope that that's been helpful as a quick overview of Ruskin, some of the capabilities that it has, and be happy to move into questions.
We've had a couple good questions that have come through, and we've been answering them as we're going. I think we should wait about 10 seconds or so and see if anyone wants to type in new questions or ask them. They can unmute themselves and ask them verbally, and then if there's nothing new, then we can run through some of the ones in the chat session.